We are a team working on water desalination through advanced vapor compression. The students who worked on this project are part of Dr. Mark Holtzappel's Engineering 491 class, and we represent one of 3 teams. The 3D modeling team will be conducting this presentation. The issue we are tackling is the global water crisis. Since 1900 to 2016, 11.5 million people have been killed by major droughts worldwide. And today, 1 in 9 people lack access to fresh drinking water. That's around 785 million people. In many developing and third world countries, women and children are usually in charge with collecting water from miles away instead of going to work or attending school. This further perpetuates the cycle of poverty. Water usage today is not a sustainable system, and the increasing population, those who are most affected are those who use the least amounts of water, as can be seen in the following graph. This shows the average daily water usage per person in gallons and liters in the following countries. And as can be seen here, the United States uses most of fresh drinking water. However, those who are most affected by extreme drought conditions are those who use the least. This is Palmer Drought Severity Index data from June 1960. And this is Palmer Drought Severity Index data from June 2020. These were taken on the same months, but decades later. As you can see here, the areas that are now there are now areas that are more exposed to extreme drought conditions. The following slides introduce our team's solution to this.
Howdy everyone, my name is Saransh and I would like to show you my 3D animated model that I made for our project this semester. So to start off, our feed water goes through a sand filter which removes the excess dirt out of it, and the sand filter consists of anthracite, sand, garnet and gravel. After which our feed water goes through a series of pumps which pushes it through a sensible heat exchanger which exchanges heat from the product that we produce, which is in this case is brine and the distilled water, and the energy difference will be used up will increase the efficiency of the system. After going through the sensible heat exchanger, there's a slight increase in temperature and goes through the latent heat exchanger, which we'll now discuss further. So the latent heat exchanger has the relatively hot feed water coming in, after which it goes through these tubes and it heats up. So as the hot water becomes steam, it is of low pressure and it is caught up at the back through these split pipes. And these split pipes take it to the compressor, which takes it from the low pressure region to the high pressure region where it heats up the coming in liquid, and distilled water is collected from the sides as condensate and it goes through this manifold. Meanwhile, the salt water gets concentrated further and further into as we go through the different effects, and it is collected at the right side. An advantage of the system is that the heat exchanger slides out and the tubes are replaceable. So once there is a lot of gunk out there, so we can just easily replace the tubes, and it is very easy to replace as well. So that is how a latent heat exchanger in this system works. So coming back to the whole system is connected together with these 10 effects. An advantage of using this sort of system is that all of them can be put in containers and can be transported into different locations where there are cases of drought, for example, where they are needed immediately, and so the whole thing is modular and it's on a concrete pad. That's the only thing that has to be constructed beforehand, so that's a huge advantage. And usually these systems don't work that way. There is a lot of reverse osmosis which requires a lot of expenses, and this system doesn't cost as much, as will be discussed by my teammates. Meanwhile, in the whole overall system, we can see that the distilled water is coming out at the back and it is connected to a single pipe, and the brine, which is concentrated, is being taken out from the last effect. It is really concentrated, it is 99% concentrated, and it is much more concentrated than usually we get from reverse osmosis or other treatments. So now these two liquids are really hot, So they can use we can use the energy through the sensible heat exchanger again and convert it back into their liquid forms, because there are some vapors present as well. So they will be taken out and they will be extracted and they will act as the output of our system. And that's how our system works. And the advantage is that we can insert multiple unit cells into this system and make it even bigger than it is already. And the output produced is really pure, and the brine itself can also be processed further, and we can extract the different elements out of it. Thank you for your time.
We would like to quickly compare some of the other desalination alternatives and make a quick cost analysis. These numbers were derived from reports provided to us by Dr. Holtzapfel, who was our mentor in this research. So comparing multi-stage flash, which is the most common method of desalination in the Middle East, and reverse osmosis, which is the most efficient one, we are advocating for advanced vapor compression desalination, or AVCD, and we are estimating a higher recovery rate of almost 90% of that seawater being actual accessible pure water, with salt concentration in the product of particle per notion of almost 2 to 10, energy consumption being low, and the chemical cost to maintain the equipment being negligible. And we do indeed have no brine pollution, which is one of the biggest difference from the multi-stage flash and reverse osmosis, as we are looking to harvest this brine and actually profit from the minerals that are contained in this seawater. So a quick cost analysis: in order to maintain the plant, we're estimating that the total cost will be around 50 cents per meter cube, which would come to around $7 million per year. And these are making the assumptions that we do have access to natural gas at $3 per gigajoule. We are financing with a 30-year bond at 2.3%, which is not far from our current values, and fixed capital investment is of around $50 million, and water recovery, like I mentioned earlier, will be 90%. And comparing this to other reverse osmosis facilities, we do fall within one of the cheapest alternatives of these desalination processes. And to continue, as I mentioned earlier, we are looking into harvesting the sea salt value and making a product out of this. And some of the main components of that sea salt are, and the sea salt mixture would be sodium chloride, magnesium chloride, hexahydrite, potassium chloride, and lithium chloride, which the product values are giving here. And from these, we can measure the contribution to value of sea salt per ton. And we're estimating that contribution to be around $117. And if we compare this, this graph is drawn to scale. So if we compare the composition of sea salt being 35 grams of salt per kilograms of solution, we're estimating that with 1 ton of salt, there will be 30 tons of water provided within that ton of salt. And if we do sell this water for 50 cents per ton of water, it will give us 13.80. And if we compare the prices, we see that salt water is worth almost 8.5 more than water. And this makes us question: are we in the salt business, or if we're in the water business? And regardless of what the answer is we don't only provide a great alternative of clean water, but the way we're dealing with brine, yes, and a great alternative of harvesting the minerals and even making a profit, whether it be high or not.